Hi all. So in this video, we briefly review the computation of the polar rotation angle on a two-dimensional unsteady velocity dataset. So in the previous video, we showed how to compute the FTLE, so the finite time Lyapunov exponents, on a two-dimensional for a two-dimensional velocity field. In this video, we focus on the polar rotation angle. Now, compared to the FTLE, which is a diagnostic which reveals hyperbolic flow structures, the polar rotation angle is a diagnostic which reveals elliptic flow structures. So what we generally intend by elliptic flow structures are, for example, vortices in the ocean. Now, both the FTLE and the polar rotation angle rely on the previous computation of the gradient of the flow map. So the polar rotation angle, the folder of the polar rotation angle is structured similarly as the folder of the FTLE. So we've got the main, we've got a main folder which contains simply the main notebooks, and then we got this notebook here which is called PRA. What this notebook does is it computes the polar rotation angle given the gradient of the flow map. So let's just briefly reveal what the polar rotation angle actually is. So given so you have a trajectory, this black one, from T0 to T, for example, and you can compute for this trajectory the right singular vectors, C1 and C2, of the gradient of the flow map, and also the left singular vectors, eta1, eta2 of the gradient of the flow map. What the PRA simply expresses is you can see that this frame, which you can view as a C1, C2 frame, gets rotated into the eta1 and eta2 frame. So all these are unit vectors. And what the PRA simply does is it computes the angle between C1 and eta1, or similarly, the angle between C2 and eta2. So the angle, of course, is the same. It doesn't matter if you take C1 or C2 for the computations. Now, generally, we prefer working with C2. So we prefer working with the most stretching direction, simply because the singular value computation of these eigenvectors is numerically more stable. To take a look at what the function does, so what this PRA function does, it simply takes as input the gradient of the flow map, which is a 2 × 2 array, basically, does the SVD computation, so the singular value decomposition. P is an array which stores the left singular vectors, Q is an array which stores the right singular vectors, and sigma and sig is simply an array which stores the singular values, which we do not need, however, for this computation. And then what we do is we simply compute. So we take the inner product of the most stretching left and right singular vectors, and then we simply output the angle. Now this condition here is just there to ensure that the inner product is not exceeding 1. What might happen sometimes is that due to numerical inaccuracies, it might be 1.000001, so we're just like tiny above 1, and of course then you cannot take the Arcus cosine from a value above 1. So this is just like to ensure that this condition is satisfied, and then you just simply compute the angle between these two vectors. So it's actually pretty simple. Now, if we go back to the main notebook, we again focus on the Abyssal dataset, so on the Agulhas region. The main notebook is structured as the FTLE notebook. The only difference that here we need to import. So we need, of course, to add the PRA folder to the current path because we want to have access to the functions stored in this folder. And then the first steps are again the same. You just like input data, define parameters, define domain of which you want to compute the PRA, and interpolate the velocity field. And then the next step would be to compute the PRA. Now, before computing the PRA, you first need to compute the gradient of the flow map. Then you need to basically need to pass this gradient of the flow map into the PRA function, and there you then compute the left and right singular eigenvectors, singular vectors, and then from the singular vectors you can then compute the PRA. So the script is structured exactly the same. So these are the structure of these sections exactly the same as in the FTLE. So we'll not go through it. The only difference that here, instead of having a parallel /FTLE function, we've got a parallel /PRA. Parallel, why? Because we use parallel computation. So we take all the initial conditions, put them into separate batches, and parallelly compute the PRA for these initial conditions. And again, in this PRA, so you first need to compute the gradient of the flow map. Then you just need to extract the gradient of the flow map from the time t0 to tn. So because this grade f map simply stores the gradient of the flow map over all times, but you're just interested of the gradient. You're just interested on the gradient of the flow map from t0 to tn. So from the initial to the final time. And then you simply pass this, this array into this PRA function. So of course, here you need to iterate over all the initial conditions and then pass the gradient of the flow map into the PRA function, and you get the PRA out of it. If you do this and plot the results, you see that you have, you get the following structures. So elliptical flow structures, or elliptic LCSs as they are called, elliptic Lagrangian coherent structures, are identified as regions where you have these concentric tubes, basically. You've got these concentric elliptic features of the PRA. So this here would be like, would for example be considered as a vortex. This one would also be considered as a vortex, and this small guy here would also be considered as a vortex. So this is simply a pre-FOSS diagnostic to reveal vortical flow structures. It's basically the analogon of the FTLE, but for the elliptic flow structures. The important thing to note is that the PRA is objective in 2 dimensions. However, if you go to 3 dimensions, then the PRA is no longer objective. With that, I want to thank you for this, for listening, and feel free to email me or to ask any questions if you want.